Hello guys and welcome to this particular exam question. It's 2015-2016. Now we are going to look at how to find the eigenvalues and eigenvectors for the equation ax equal to lambda x, where A is this 3 by 3 matrix that we're given here. So let's dive into the solution. So when you're given ax equal to lambda x, this is going to evaluate to ax minus lambda x equal to 0. Then when you factorize x, you have a minus I lambda, or a minus lambda I of x equal to 0. So this is equation 1. It's called the eigenvalue problem, or eigenvalue problem, or the eigenvector problem. Okay, so this helps us to actually form what we call a characteristic polynomial or characteristic equation, and with that we can get our eigenvalues. So after getting the eigenvalues, we use the eigenvalues to get the eigenvectors. So we are going to what form a minus what lambda I. So this is our A matrix. So you have A is equal to or let me just put it like this, A minus lambda I, right? So our A matrix is, I'll borrow what we have on top, 2 minus 1 minus 1, 0, 4, 2. And we now have 1 minus 1, 0. Okay, then minus I lambda. So lambda into your identity. Your identity will be of equal size with A. So you have a 3 by 3 identity matrix. Okay, so what will this evaluate to? So this is going to evaluate to 2, 0, 1, minus 1, 4, minus 1, and minus 1, 2, 0. Then, sorry, let me put that 0 very well. Then you now have minus lambda, lambda, lambda. You have 0, 0, 0, 0, 0, 0, like this. So when you evaluate this carefully, term by term, you have 2 minus lambda. Then every other term will remain as it is. So only the diagonal terms will subtract lambda. So you now have minus 1, minus 4. So instead of which to write 4, we'll have 4 minus lambda. And we now have 2. Then 0 minus lambda is minus lambda. So with this, this is how we normally get this matrix that you see here. So our A minus I, or A minus lambda I, corresponds to this 2 minus lambda 0 1, then minus 1 4 minus lambda. Then you now have I forgot one element, which is this one. You now have minus 1 here, and you now have minus 1, you now have 2, then you now have minus lambda. Okay, so this is our new matrix. So with this new matrix now, we are going to get the characteristic polynomial. To get the characteristic polynomial is the polynomial that will yield a characteristic equation which we can use to find the eigenvalues. The roots of the characteristic polynomial are the eigenvalues. Is that okay? So you can get that by taking the determinant of this particular matrix. Okay, when you take the determinant of this matrix like this, and equating it to 0, that is how you get your characteristic polynomial. So we are going to expand along the first row. we're going to expand along the first row. The first row has a 0 element, so it will make our expansion easy. So I have 2 minus lambda, then into 4 minus lambda minus 1, then 2 minus lambda, like this. Then 0 times the minus of 0, which will be 0, then you now have plus 1 times the minus of 1, which is going to be minus 1, 4 minus lambda, you now have minus 1 and 2 equal to 0. Is that okay? So we are going to solve it like this. So you have 2 minus lambda here. Then if you expand, you will have minus lambda into 4 minus lambda. Then this minus this times this is going to give you a plus 2. Okay, so this times this minus this times this, since this one is negative, it will become positive, and plus we have a bracket. 2 times negative 1 is negative 2, and minus the product of these two, which is going to be plus 4 minus lambda. Is that okay? Equal to 0. So I'm going to do some manipulations on this side so that we'll see what is happening. So 2 minus lambda into, so if I expand these brackets, I'm going to get lambda times minus lambda will give me lambda square, and lambda times minus lambda times minus lambda is lambda square, minus lambda times 4 is minus 4 lambda. Then you now have plus 2. Is that okay? And you now have plus, when you evaluate this, you will have minus 2 plus 4. Minus 2 plus 4 is going to give you 2. Then you now have minus lambda equal to 0. Is that okay? So you can see that 2 minus lambda is common, and we can factor it out. So 2 minus lambda is going to be factored out, and we'll now have lambda square minus 4 lambda plus 2. Then when you factor it from this term, you will have this. Then when you factor it from this term, you will have plus 1. Is that okay? Equal to 0. So I hope you understood how we factored out this term and we got this. So with this, we have 2 minus lambda, and we'll now have lambda square minus 4 lambda plus 3 equal to 0. So with this, we have gotten two separate terms that we can equate to 0. But let's try to factorize this. This is 2 minus lambda, and if you factorize this properly, you're going to get lambda minus 1 and lambda minus 3, because you're looking for two terms that when you multiply, it will give you plus 3, and when you add, it will give you negative 4, and those two terms are minus 1 minus 3, okay, equal to 0. So with this, we have 2 minus lambda equal to 0 implies lambda equal to what? 2, or lambda minus 1 equal to 0 implies lambda equal to 1, and lambda minus 3 equal to 0 implies lambda equal to 3. So our eigenvalues is equal to 1, lambda 2 equal to 2, and lambda 3 equal to 3. So for a 3 by 3 system, we'll have 3 eigenvalues, and so on and so forth. For a 2 by 2 system, we'll have 2 eigenvalues, and so on and so forth. So these are the eigenvalues. So how do we calculate the eigenvectors? So calculating the eigenvectors. So we'll start with refer to the equation, your a minus lambda I equal times x equal to 0. Okay, so we're going to make reference to this equation. Remember, we established this equation at this point. This is the eigenvalue problem, so we are going to make reference to it. So for each of this problem, we've already gotten the form of this matrix. So we are going to say, let our x matrix take the form, let it take the form A1, or let's just take a general form A, B, C. Okay, so this is called our eigenvector. general. Okay, so let X take this particular form. So we are now going to start evaluating our matrix, or I'm sorry, evaluating our eigenvectors, but we need to recall that A minus lambda I has already been gotten. So A minus lambda I was gotten to be from what we have over here at this point. Okay, so that we'll not have to do the solving again. So 2 minus lambda 0, 1. And I know there is a 4 minus lambda. I know there is a minus lambda. There's a minus 1, there's a minus 1, there's a minus 1, and there's a what? There's a 2. Okay, so there's a 2. So this is our matrix. So combining these two, we'll begin to solve for our eigenvalues as follows. So let me just copy them both, and we'll start solving. So when lambda 1 is equal to 1, so we are going to solve the eigenvalue problem. Okay, we are going to obtain the first eigenvector. So we solve a minus lambda 1 times I multiplied by a certain x1 equal to 0, where x1 is the eigenvector associated with lambda 1. So this arrangement will just yield something like this. So it will yield this. So you have a 2 minus lambda. This time around, instead of me to say 2 minus lambda, I can just start evaluating it directly. So 2 minus 1 is going to give me 1. I'm evaluating this matrix here, and you now have 0, and you now have another 1, and you now have minus 1. So 4 minus lambda 1, which is 1. 4 minus 1 is 3. Then you now have minus 1. Then you now have minus 1, 2. Then minus lambda is minus 1. So multiplied by x1. x1 is going to be, remember we called x, the general form is ABC. So x1 is going to be an A1, a B1, and a C1. Okay, then you can call it 0. Now this 0 is also a 0 vector that has the same length, the same number of entries as or the same dimensions as the vector x. So you can just call it 0, 0, 0 like this. Okay, so how do we evaluate the relationship between A, B, and C? So there are many ways to do this particular stuff. You could even use elementary row operations, but I'm going to stick with a method that you actually know and you're actually comfortable with for this problem. Then in other tutorials, I'll introduce us to how to use elementary row operations to obtain the relationship between A, B, and C. So for now, let's just expand, okay, and get 3 equations. So if we expand this versus this, we are going to get a1 plus 0 times b1 is 0, then plus c1 equal to 0. Then if you expand this one, you're going to get negative a1 plus 3b1 plus or negative c1, okay, is equal to 0. Then finally, if you expand the third column, you get negative a1, okay, and you now have plus 2b1, and you now have negative c1 is equal to 0. So you have these 3 equations. Now you have to consider that this second equation and the third equation, you could actually modify them like this. So you have a1 plus c1 is equal to 0. If you divide through by minus 1, okay, if you divide through by minus 1, you get a1 plus a1 minus 3b1 plus c1 equal to 0, and a1 minus 2b1 plus c1 equal to 0. Now the first equation already suggests to us that a1 plus c1 is equal to 0. Okay, the first equation already suggests to us that a1 plus c1 equal to 0. a1 plus c1 equal to 0. So you can substitute this a1 plus c1 equal to 0 into this second equation or this third equation. Is that okay? So when you substitute it in second equation, so we call this equation 1, equation 2, equation 3. So put let me just say put a1 plus c1 equal to 0 in equation 2 so that we can find the value of b1. Okay, so in equation 2 you have a1 plus c1 minus 3b1 equal to 0. So since a1 plus c1 is 0, you have 0 minus 3b1 equal to 0. So this implies that b1 is equal to 0 over negative 3, which is equal to 0. So a1 plus c1 is equal to 0 and b1 is equal to 0. Therefore, how do we now establish the relationship between three of them? So a1, we've gotten that b1 is equal to 0 and a1 plus c1 is equal to 0. So let me express c in terms of a. So c1 is equal to negative a1. So with this, you can now assume a value. Okay, you can assume a value. See, so if a1 is something like 1, what will c1 be? So c1 will be what? Minus 1. So with this, you have gotten an arrangement for x1. Okay, so for x1, when lambda 1 is equal to 1, will be equal to our a1, b1, and c1. And a1 in this case is 1. Okay, and b1 is 0 and c1 is minus 1. Okay, so and this is how to get the first eigenvector, okay, arrangement. So I hope you understood this. So if you don't understand this, I'm going to do for the second one, and definitely you will understand along the line. So let's solve for lambda 2 equal to 2. Okay, for lambda 2 equal to 2, we'll solve the eigenvalue problem a minus what? Lambda 2I multiplied by x2 equal to 0. So in this case, our a minus lambda 2 will be, for this matrix over here, let me just copy it, Control C. So I'm going to place it by the side here. So this is our reference matrix over here, our a minus lambda I. So this is it. So we are going to be subtracting 2 anywhere we see lambda. Is that okay? So when we do it for this first place, we are going to get 2 minus 2, which is 0. So you have 0, 0, 1. Okay, then your x2 evaluates to a2, b2, and c2, just like we did in the first instance. And your 0 is a 0 vector consisting of 0, 0, 0. So here is minus 1, here is minus 1. So 4 minus lambda, 4 minus 2 is 2. Then you have 2 here. Then you now have minus 1. And minus lambda is going to be minus 2 since we are working with lambda equal to 2. So we have this system. And as before, you can just expand this system. So 0 times a1, okay, is 0. We have 0 plus 0, then plus, we now have c2 equal to 0. Okay, when you expand this by this, you get your equation 4, because I've already gotten 1, 2, 3 above there. And if you expand this versus this, you're going to get minus a2 plus 2b2, and you now have minus what? C2 is equal to 0. Take note that equation 4 gave me C2 equal to 0. So this is equation 5. And equation, the last expansion is typically just repeating the third expansion. So you can write it or you can choose not to write it. But let me just write it for sake of writing sake. So you have a2 minus a2 plus 2 b2 and minus, okay, it's not really the same, but what does it matter? Let's find out. We now have 2c2 is equal to 0 is equation 6. Okay, so we already know that c2 is what? 0. So you can choose to work with either equation 5 or equation 6. The most important thing is that these two places are the same. So I can put C2 in any of 5 or 6. Okay, so these two and these two did not change in 5 or 6. So since the value of C2 is 0, I'm going to get, whether I put it in equation 5 or equation 6, I'm going to get this equality minus A2 plus 2B2 is equal to 0. Is that okay? So what does that imply? That your A2 is equal to 2B2. Is that okay when you do the maths? Now you can choose a base value just like we did previously. So choosing a base value. So when you're choosing a base value, choose a small base value as much as possible, or a value that will prevent you from doing fractions or complex calculations. So the simplest is let B2 be 1. So if B2 is 1, what is A2? A2 will be 2 times 1, which is equal to what? 2. So we have 3 arrangements already from this eigenvector. A2 is 2, B2 is 1, and C2 is 0. Therefore, our x2, which is A2, B2, C2, the base form of our eigenvector is 2, 1, so and what? 0. Okay, someone else might have gotten 1 over 2. Sorry, someone else might have gotten 1 over 2 and 0. It's still the same thing. Is that okay? You just divided through by 2. So someone else would have represented his own as 2t, then you now have t and 0. So it's still the same thing where t is an arbitrary constant. So it doesn't matter how you do it. All we are just interested in getting is the base form and this coefficients. Is that okay? So this is our eigenvector when lambda is 2. And we're now going to repeat the last one. So I can leave you to try that one. You can pause the video and try that one by yourself. So once you're done, you could unpause it and see what I'm going to get when I solve for lambda 3 is equal to 3. So we're going to repeat the same thing. So solving our a minus lambda I as usual. So we are going to solve the eigenvalue problem, a minus lambda 3 I multiplied by a certain x3 eigenvector which we want to find and equal to the 0 vector. So this will now yield this. The a minus lambda 3 is anywhere you see lambda, you subtract it, you put 3. So 2 minus 3 is minus 1, and you now have 0, you now have 1, then you now have minus 1. 4 minus 3 is 1, and you now have minus 1, then you now have minus 2. Sorry, this is a minus 1, and you now have 2, and minus lambda is going to be minus 3 since we are dealing with when lambda is 3. So our x3 can be a3, b3, and c3 in this case, and you can call this a 0, 0, 0. Okay, so when you have it like this, what next? So you can write the equations. When you expand this first place, you're going to get minus a3 plus this times this is 0, then this times this is plus c3 is equal to 0. So this is your equation 7. Then you now have what? Again, if you expand the second one, you have minus a3 plus b3, then minus c3 is equal to 0. This is your equation 8. Then finally, in expanding the last one, you have minus a3 plus 2b3 minus 3c3 is equal to 0. And this is equation 9. So we want to find a meaningful relationship from these identities. Okay, so we're going to copy it and go work with it up here. All right, so how do we find the identities? So we already know that from this particular side of the equation, minus a3, okay, plus c3 is equal to 0. So I hope we're together on this. That's from the first part of the equation. So what can we do with this piece of information? What can we do with this piece of information? So you can actually take it like this. Five, four, three, two, 1, 0. So if minus A3 plus C3 is equal to 0, it means that A3 is equal to C3, right? So we can keep that as a reference. So let's go to equation 8 and see what we can get. In equation 8, if we make B3 subject of the formula, you got your B3 to be A3 plus C3. If you send this one over to this side and this one over to this side, is that okay? So now that you've gotten this, you're now going to put B3 in 9. So when you put B3 in 9, you're going to get minus A3, okay, plus 2 into, you have A3 plus what? C3. Instead of 2 into B3, you've replaced it with 2 into what? A3 plus C3, then minus 3C3 equal to 0. Okay, so when you solve, you're going to get minus A3 plus 2A3 and plus 2C3 minus 3C3 is equal to what? 0. Then when you solve this particular case, minus A3 plus 2A3 is going to give you A3. Then 2C3 minus 3C3 is going to give you minus C3 equal to 0. So you see that by solving this last equation, A3, okay, is equal to what? C3 again. So A3 is equal to C3. So let's choose base values. So I can choose a random value. For instance, I can say C3 is equal to K. So if C3 is equal to K, A3 is equal to what? K as well. Okay, so my B3 is A3 plus C3, which is going to be K plus K, which is going to be 2K. So with this, I have gotten what? A base vector for V3 for my X3, which is corresponding to A3, B3, and C3. So my A3 is K, my B3 is 2K, and my C3 is what? Also K. Okay, so if K is an arbitrary constant, if we make K 1, then we can have the simplest base vector for x3 to be 1, 2, 1, like this. Is that okay? So we have final eigenvector here. So I hope you understood. Let's just summarize. So in summary, we have lambda 1 equal to 1. So our eigenvector corresponding to that was, we got I guess a 1, 0, minus 1, if I can still remember. So we had lambda 2 equal to 2, and the eigenvector associated with that, can you still remember? We got a 2, 1, 0. I hope I can remember that correctly. A 2, 1, 0, right? Yeah, 2, 1, 0 over here. Then finally, when lambda 3 was 3, we got our x3 to be the basis form as 1, 2, 1. Is that okay? So this is what we have as our eigenvalues and eigenvectors for the given system. Now, these eigenvalues are actually legitimate because if you substitute them into this equation, you will see that they works. Like the value of A is 1, the value of B is 2 and the value of c is 1. So if you plug it into this equation, you're having something like minus 1, then plus 2 times 2, which is what? 4. Then you now have minus 3, which gives me it gives me 3 minus 3. Minus 1 plus 4 is 3 minus 3, and gives me 0. So it satisfies. Is that okay? So the third eigenvector satisfies this equation. So you have 1, 2, then 1. So 1 minus 1 plus 2 will give you 1, and 1 minus 1 will give you 0. And since a and c are equal, minus 1 plus 1 is going to give you 0. So it's actually legitimate. When you get your eigenvectors, you can plug it back into the system of equations that yielded that particular eigenvector and confirm if it gives 0. If it doesn't give 0, then what you got is not correct, so you need to tabulate and solve again. So I hope you understood this particular question on eigenvalues and eigenvectors, and don't forget to like and subscribe to my channel, and stay tuned for future updates. So thank you very much, and see you in the next video.